Good evening, everyone. I welcome you all to the problem solving session of the NPTEL course on ice engines and gas turbines. I am Pradeev E. I'm one of the teachers for this course. So we will start from the assignment problems. So these are the previous year assignment problems. The function of piston rings in internal combustion engine is uh, used to prevent piston from the air, dissipate heat to cylinder walls, seal the cylinder, all of the above. Can you, if you know the answer, you can type in the chat box. So all of the above. So piston rings is uh, piston driven from the rear, so that if we do not have the rings and we have only piston, then the entire gear will be on the entire piston. So then replacing the piston will be expensive than replacing the rings alone. So that is one thing, and then dissipate the heat to the cylinder walls through the piston only. The heat is transferred, and seal the cylinder. So if there is no piston rings and then you have only the piston, then there should be some gap between the piston and the cylinder liner, so the air can or the gas can flow through the passage. So to avoid that, we have rings which are flexible, and then it will appear with the force, it will have a sealing surface. So if you take the ring, so this could be a ring from the top view. You have to expand this, uh, put it away, and then put through the cylinder grooves. So the grooves will be so you expand and put through this, and then once it comes to this position, then you can release the expansion. So then it will be held at the force. So if this is the liner, so the liner will be something like this, and the gas pressure mainly acts on the piston, but it is sealed and prevented from going towards the cylinder case. The weight of the SI engine is relatively higher than that of the CA engine. This statement is true or false?
False.
Can you say why it is false? Why CA engine is heavier than SI engine? So what is the compression ratio that we have in SI engines?
4 to 10.
Sorry?
4 to 10.
1 to 10?
4 to 10.
4. Okay. Yeah. So in some advanced SI engines, it can go up to 11 or 12 maximum. And what about CA engine?
12 to 20.
12 to 20. So then which will have very high pressures inside? SI engine or CA engine?
CI engine.
CA engine will have high pressure. So that means the piston material, or the strength of the piston has to be high enough. So that means you need to have a thick piston. And similarly, the liner, the whole cylinder, this material we put here also has to withstand all the high pressure. So then we need to have a heavier engine. So that is why CA engine is always heavier than SI engine. Which of the following statement is true for CA engines? Fuel and air are introduced into the chambers of CA engine as gaseous mixture. CA engine is based on DC cycle. CA engine has compression ratio between 12 to 20, spark plug is necessary to initiate combustion in CA engine.
Sir, 1, 2, 3 statements are useful.
1, 2, 3.
Yes, sir.
If 1 is correct, fuel and air are introduced in the chambers of CA engine. 1 is not correct.
Okay, sir.
Yeah. So in CA engine, in SA engine, okay, this is intake, this is exhaust, we have piston, and then we will have something called spark plug. So in intake, we have fuel plus air going in, and then at the end of compression stroke, this spark is ignited, and then combustion starts. So that is why we call it spark ignited engine, spark ignition engine. In CA engine, so and this fuel, we use fuels like gasoline that will have high resistance to ignition. So that is why even after compressing the fuel and air mixture with the high temperature and pressure after the combustion, it is not able to combust on its own. That is why we introduce a spark plug spark to initiate the combustion. Whereas in case of CA engine, the structure is everything the same. We have injector which will spray fuel into the cylinder. We have exhaust intake, and only air is entered injected in the intake port. So after at the end of compression stroke, now the fuel pressure and temperature of the air inside the cylinder is high, and at this time we inject fuel, and this fuel can catch fire with the compressed high temperature and pressure, and that is why it is called compression ignition engine. It can ignite only based on compression. And now in case of gasoline engine, if you have very high compression ratio, the even before the spark it can start igniting, which is not desirable. Say it can start to ignite at say 90 degree, sorry, or yeah, 30 degree or 60 degree before TDC at very early stage. So then this is um, not desirable. That is why we restrict the compression ratio to say 10 or 12 maximum. But in case of CA engine, it is better to have more compression ratio. Then we will have a good condition for the burning of the fuel. So that is why we go up to say 20 compression ratio. Fourth question, compression ratio can be defined as clearance volume by soft volume, clearance volume plus soft by clearance, or clearance plus soft by soft. What is compression ratio? I think we have solved some problems in the last class with compression ratio.
Clearance volume versus volume of clearance.
Yeah, this is it. So if you have a motorcycle, Suraj Mandale has raised the hand. If you have any questions, you can unmute yourself. So compression ratio is volume at 1 before compression and after volume before compression divided by volume after compression. Suraj, you have some questions? So volume before compression is this full volume. V1 is this full volume, and V2 is volume at the end of TDC, at the end of substance compression stroke, that is at TDC. So at TDC we will have only clearance volume, and at state 1 we will have clearance volume plus swept volume. So this is swept volume and this is clearance volume. If an engine is classified as two-stroke engines, then number of working strokes per minute for two-stroke cycle are one half the speed of engine in rounds per minute, twice the speed of engine in rounds per minute, equal the speed of engine in rounds per minute, 4 times the speed. This is the right answer. For a two-stroke engine, number of working strokes per minute.
Square of 10 1.
How? This is a two-stroke engine. In two-stroke engine, we will have some delivery port, a transfer port, connected to the crankcase. And air is given inside this fuel plus air up based on the SI of the engine, and then this is the exhaust port. Now when the piston moves upward for initially sorry, when the piston moves down from TDC to DDC, it will compress the mixture in the transfer port or in the crankcase in this region, and then when it uncovers this port, then the fuel and air mixture enters inside. So during downward stroke, and this will also be the exhaust stroke for the previous cycle. The hot gas will start exiting through the exhaust port, and then while compressing, it will once it uncovers this region, this intake port, then it will start compressing. Till then it will be only a gas sucking process, and then while it moves up, say the first few crank angles, it will be in the gas exchange portion, and then it will start compressing, and then similarly while expanding till this point, it will be power stroke, and then it will start with the gas exchange. But there will be only two strokes needed for one complete cycle. So that means for every revolution there will be one engine cycle complete. So that is equal to the speed of engine. Only in a four-stroke engine, so only in a four-stroke engine we will have intake, compression, power stroke or expansion stroke, and then exhaust stroke. In case of two-stroke, these two are clubbed together and these two are clubbed together. Okay. So there will be only two steps. And so compress will be two. In four-stroke SI engine, the pressure inside the combustion chamber during suction stroke is below atmospheric pressure equal to atmospheric pressure above or none of the mentioned.
So above the atmospheric pressure.
How?
The carburetor is pressurizing the air and fuel before it is given to the chamber, fuel system chamber.
Carburetor pressurized air. Carburetor function is just to add the fuel, right? Fuel and mix with it.
Yes, but the same is some pressure will you provide to the engine system.
No, only in turbocharged engine you will have intake manifold pressure higher than the atmospheric pressure, and then during intake stroke you will have pressure more than the atmosphere. But otherwise, in case of the general engine, uh, when you take air inside the, when piston is moving down, air from the say intake manifold, this is intake manifold, has to enter inside, and because the piston is moving down it will create a partial vacuum, and then because of this this pressure P less than the P atmosphere, air flows from the manifold to the combustion chamber. So this is below atmospheric pressure. And during exhaust stroke it is the other way. Piston will be moving upward and it will try to compress the exhaust gases, but the port is open, and because of this little high pressure, the from high pressure of the combustion chamber, the gas flows through the manifold pressure, manifold which is exhaust manifold, which is almost near atmospheric pressure. Do you have any questions?
No,
Intake valve opens slightly, dash piston is set dash, and closes slightly, dash of piston is set dash. So intake valve open happens before TDC, after TDC, before TDC, after TDC. Ideally, when does the intake valve opens? Intake stroke, how does it happen? It is from DDC to TDC or TDC to TDC?
TDC into DDC.
TDC to TDC. The piston moves down. Now, so that means it is either before TDC or after TDC, right? Before TDC, after TDC. Intake valve has to open slightly before or after TDC. So now can you say if it is before or after?
So option B.
B, before TDC. Why?
D, sir. D.
D.
After TDC, before DDC.
And why?
For the intake, it should be open after the moving down, and it should be closer before the reaching the DDC. Because the next stroke will be compression.
Next stroke is compression, but For practical reasons, we always open slightly before TDC and then close it after TDC. Why? Because um, during TDC, the suction TDC or the intake TDC or suction TDC, this is where the exhaust gases is also moving out, right? So the piston is at TDC and the intake valves and all will be operated by cam. So the cam lift will be cannot be like we start at certain point the valve lift. So lift means like this is a closed position. A closed position, it is there is no space between the valve and the head, and at open position, say here there is some space. So this is called as valve lift. So say this is crank angle. The lift cannot abruptly start and open to go to a very high lift. So it has to gradually increase and be there, stay for in the maximum position and then come down. So say this can be the TDC point. So the our effective stroke will start from the TDC when the piston moves from the TDC to downward point. So if it starts moving from there and if the valve is just started opening, there is no, we don't get the benefit. We don't get the proper air coming in. So that is why we need to start opening a little early so that at TDC and when the piston starts moving downward, we have sufficient lift for the gas to come in. And similarly, when we close, we close after BDC. This is because when the piston is moving downward at a faster rate, there will be some subatmospheric pressure inside the compression chamber. Say at when this is at BDC, this will be, say, pressure will be around, say, 0.8 bar, whereas atmospheric pressure is 1 bar in the intake manifold. Now if you allow it to stay there for some time, this can keep increasing, the flow will be still there, and then this will go to, say, 0.9 bar. That means we are taking in more air just because we are allowing it to stay there. uh, so to make it happen, we keep the valve open for some more time after BDC also. So after BDC, it will start, the piston will move upward, but it is at a slower rate because around the TDCs the piston movement is slow. That is from the slider crank mechanism thing. So after BDC, it will be slightly moving upward, but still the pressure inside the thing is increasing. Inside the compression chamber is increasing, and the air is still flowing inside. So to take the most of the air inside, we have to close the intake valve little after BDC, and this is the reason we have this valve timing. So while starting, we start before TDC, and closing, we close it after TDC, after BDC. Any questions?
No, sir.
Then next one, which of the following statement is or correct? Petrol engine occupies more space than diesel engine for same power output. Thermal efficiency of 4-stroke engine is more than the thermal efficiency of 2-stroke engine. If intake air increases, efficiency of IC engine will decrease. As temperature increases, efficiency of IC engine will decrease. With increase in cutoff ratio, thermal efficiency of diesel cycle have fixed compression ratios will decrease. Which of the following statement are correct?
So 1, 2, and 4.
1, 2, and 4. What do you say? how petrol engine occupies more space than diesel engine.
Also, same operator to describe the offtake and the system state. Okay.
No, actually, if you consider petrol engine,
Option that is correct.
sorry,
I think option third is correct.
third is correct. Huh? Okay, let's start from first option. Do you have any comments on why petrol engine occupies more space than diesel engine for same power output? So this you can take as compression ratio is constant for both the petrol engine and diesel engine. Okay, so then for same compression ratio, the efficiency of Otto cycle will be greater than the efficiency of the diesel cycle. So that means you need to burn more air in less air in Otto cycle. So m dot a can be lesser compared to m dot a in diesel. So you can have a engine of less smaller stroke volume. And that is why you can this petrol engine occupies less space. M dot A is less, the displacement volume is lesser, so you can have smaller petrol engine for the same power output. So this is provided compression ratio is constant, and then there is no turbocharger. So these are like basic questions when you just start learning about petrol engine, diesel engine. These are the things. But if you go for a actual practical application, then it might be different. Yeah, actually you cannot have. They don't have the same compression ratio. There will be turbocharger that is possible in diesel engine, not possible in petrol engine, and so on. Okay. Next, thermal efficiency of 4-stroke engine is more than the thermal efficiency of 2-stroke engine. Can you say why?
This is also correct.
Sorry, DC?
Second number is correct.
Correct, yeah, but why?
Because of combustion process of four-stroke engine is more.
Combustion process for 4-stroke engine is more. You mean combustion timing, duration? So these can be said with different reasons. Right? The first reason is uh, you have full entire compression ratio is usable. That means in case of 2-stroke engine, we saw like say 20% or 30% of the stroke of this piston is not used for compression. Only beyond the transfer port you use for compression. So this will lead to lesser thermal efficiency. Okay, so entire compression ratio is usable for 4-stroke engine. Now the second is scavenging issue is not here. Do you know what is scavenging? So scavenging is in this case in 2-stroke engine the
Unburnt fuel.
yeah
Unburnt fuel.
unburnt fuel. Scavenging is a process which involves unburnt fuel. Okay, the process is during exhaust stroke. I mean, during when the exhaust gas has to be expelled outside, the transfer port, the fresh air fuel mixture from the transfer port enters inside, and then that pushes the burnt gases outside. Okay, so this process is called scavenging, and during this process some air fuel mixture will also get mixed with the exhaust gas and then go out. So that unburned fuel is lost in the exhaust port, so without any useful energy output. So this is called scavenging, and this is not a problem in a four-stroke engine because uh, we have different intake stroke and then exhaust stroke, so there is no mixture of intake air and short circuiting and going to the exhaust manifold. So this is one advantage of two-stroke of a four-stroke engine compared to two-stroke. And any other thing? Like I think someone was mentioning, you have more duration for combustion. If you take both two-stroke and four-stroke engines with same running at same RPM, say 3000 RPM, this for two-stroke engine, after a certain point it will hit the exhaust port, and beyond that it cannot, the combustion is not possible because the pressure has gone down. And even if combustion is there, it is not transferred to the piston. So because of this, there is no you give less duration for less time for combustion. Whereas in four-stroke you have the entire stroke coming down, and because of this you have more duration available for combustion. So this is the third idea why four-stroke thermal efficiency is better than two-stroke thermal efficiency. Then third point, if intake air temperature increases, efficiency of IC engine will decrease. Can you say why? If intake air temperature increases, efficiency of IC engine will decrease. So what are the major losses of IC engine? So if I give 100 joules of fuel energy,
Something like this.
sorry,
Something loss.
pumping loss, okay,
Friction loss.
friction,
Incomplete combustion.
Still these are not the major losses. So if I give 100 joules of fuel energy, only say 33 goes as useful work. Next 33 and next 33, you can split into one third, one third, one third. Like these are kind of major components of the energy share. So the second major portion is heat transfer. So for air-cooled engine, the heat transfer is transferred to the air, heat is transferred to the air, and for a water-cooled engine or this liquid-cooled engine, it transfers to the coolant liquid. So this is like a one third of the fuel energy goes into the cooling, for cooling the engine. And what is the remaining 33%? So for remaining, it goes in the exhaust. The exhaust enthalpy, the exhaust temperature will be very high, say at least 600 Kelvin, even at low engine load. And at a high engine load, it can even be like 800 Kelvin or more. For SI engine, it can touch up to 600 degrees Celsius, so that is 1073 Kelvin. So one third of the fuel energy is lost in the exhaust system. Okay, so now how air temperature is affecting this. So high air temperature means at the end of compression stroke, you will end up with high temperature. That means T2 is T1 into compression ratio power gamma minus 1, right? So that means if you have a very small increase in the initial temperature, the change in temperature of say 5 degrees Celsius will account for say very large difference in the end of compression air temperature. This can say if this is just 5 degrees, this can go up to 50 degrees change. What I mean to say is the change between T1 being 20 degree or T1 being 25 degree will lead to a very large change in T2. Okay, because it is multiplied by the term compression ratio for gamma minus. Can be say if this is 500 and this can become 550. Continue. So because of the small change in increase in the air temperature, intake air temperature, there can be very high temperature at the end of compression, and then adding heat will add the temperature further, and then because of all this, the heat loss will be higher. And heat losses, like we know, during, if you consider convection heat transfer, it will be Q is equal to HA delta T. So delta T is T gas temperature or the in cylinder air temperature minus T wall temperature. T wall is the temperature of the cylinder walls, and T gas is the temperature that these after compression or after combustion, whatever the gas temperature will be. So increasing this T gas will increase the heat transfer, and then that will lead to a losses. So that is why if you increase the intake air temperature, the efficiency of the increase IC engine will decrease. The fourth point, with increase in cutoff ratio, thermal efficiency of diesel cycle having fixed compression ratio will decrease. Can you say why?
I think the fourth option is incorrect.
No, it is correct. Do you remember the formula? I do not remember. Eta diesel. Does someone remember this? This is compression ratio power gamma minus 1. Then we have cutoff ratio power gamma minus 1. So surface minus 1 into 1 by gamma. Am I right? So now you cannot directly solve. You might want to put some different cutoff ratio for same, say compression ratio can be, you can fix to 10, and then RC you can vary from 1.1, 1.2 and keep on, and then keep plotting RC and then eta diesel. Then you will see that increase in cutoff ratio will decrease the will reduce the efficiency. But we can also see why it is. First I will start with the diesel cycle. So in diesel cycle I will draw it green. The same compression ratio between 1 and 2, V1 and V2. We reach a point at 3, this is 1, 2, 3, and then expand and come back to So this is, so here I assume that I have given a heat input. Okay. So now green is Otto cycle. Now I will draw red diesel cycle. Say RC is 2. 2 means it will be almost in the so the compression is the same from 1 to 2, and the compression process will keep on going on till RC is what, V3 by V2, right? V2 is 2. So that means something like this. So if this is 1, I will have almost same. I may not end up with the same points, but something else. And now if I say V3 in the next one, V3 by V2 is 3, then I will keep going further here, then that is it. So in all this case, what I have done is I have uh, I've burned in the fuel at a later stage of the stroke. For example, first in Otto cycle, uh, I burnt all the gases or all the fuel at one point itself, at second point, and then I suddenly went up to pressure of 3, P3, which is very high. And now from this very high pressure, I am expanding till say 4, and then coming to 1. So because of this, I have got, I now the area of the under the curve, which is the work done, is very high, right? Work done for Otto cycle, I got a very high value. Why? Because I burnt all the fuel at the same point itself. Now and now because of this, my at fourth point the temperature will be very low, because I'm expand. I just combust at one point and now expanding for a long time. Whereas in case of diesel cycle, I keep on as the piston moves downward, I'm putting fuel for burning, and that means the the pressure is not increased as high as a Otto cycle, and this will lead to very low work done. And also since I am burning at a late point, the expansion is not complete, and as the expansion is not complete, then at the end of this stroke I further had some pressure to expand, but I didn't expand, and I have to leave it as a blow by loss. And because of this, the later I keep burning the fuel, the lesser there will be the efficiency. So that is what we say with the higher cutoff ratio. Higher cutoff ratio means I'm keep burning towards the um, to, along the stroke. If the cutoff ratio is very low, that means I've almost approached, I burned most of the fuel within this small region itself. So that is the significance of the cutoff ratio. As I increase the cutoff ratio, I am delaying the combustion, and because of this I lose expansion. So that is why with increase in cutoff ratio, thermal efficiency of diesel engine having a fixed ratio will decrease. Do you have any questions?
No, sir.
The sequence of operation stages of four-stroke engine is suction, expansion, compression, exhaust, expansion, compression, suction, exhaust, compression, expansion, suction, exhaust, suction, compression, expansion.
Johnson post.
Four is right. We compress and suction, compression, expansion. Next question: during suction stroke in a petrol engine, the required portion of air and fuel mixture is supplied with the help of Injector, fuel pump, carburetor, none of these.
Carburetor.
Carburetor is it. Injector and fuel pump are used for a inner diesel engine. So now, stoichiometric air fuel ratio of petrol is roughly 50:1, 25:1, 15:1, or 1:1. You do not know the stoichiometric air fuel ratio for petrol engine. So it is around 14.7:1. So approximately it is 15:1. Next, venturi in a carburetor results in decrease of air velocity, increase of air velocity, decrease of fuel flow, increase of manifold vacuum.
So increasing air velocity.
Yes. How does it increase air velocity?
The pressure will be released, so the air velocity will increase after the venturi.
No, it is in the venturi. So if you have a venturi like this, at this point and this point you consider this is 1 and this is 2. Area at 1 is greater than area at 2. That means for continuity you should be having velocity 2 should be greater than v1. So because q is constant, that is a1 v1 equal to a2 v2. Okay? And once velocity is high, with Bernoulli principle we know pressure has to be compensated. P by rho g plus v square by 2g at 1 minus equal to p by rho g plus v1 square by v2 square by 2g. So by Bernoulli principle you can say since the velocity has increased, pressure will decrease. And I think for this question this is enough. Area and pressure. The choke is closed when the engine is accelerating hot, cold, idling.
Hot.
Why?
So because the engine is enough to burn the fuel. When engine temperature is enough to burn the fuel.
No, actually answer is cold. When the vehicle is cold, the engine is cold, we will the combustion cannot sustain because all the body everything is cold. So now we need to have very rich mixture to burn the fuel. So that is why we close the choke valve. That means the more air will not go, but same relatively high fuel will go, and the air fuel ratio will be uh, lesser. That means rich in fuel, which is favorable for cold starts. So that is why we close the choke in the engine during cold starts. Lean air mixture is required during idling, starting, accelerating, cruising. Cruising. While accelerating, we need more power. While starting, like I said, for better combustion, we need to have, and then idling also to sustain the uh, engine at idling RPM is difficult, so we need to have more fuel. But while cruising, the limits of air fuel for SI engine are 8:1 to 18:1, 8:1 to 50:1, 25:1 to 50:1, 50:1 to 100. The limits of air fuel for SI engine is 8:1 to 18:1. because it is a pre-mixed compression. In case of pre-mixed compression, the flammable limit comes into picture. Do you know what is flammable limit? Flammable limit is a property of fuel. Say methane might have a different flammability limit. Gasoline will have a flammability limit. Diesel will have its own flammability limit, and so on. So the flammability limit is you have a certain air fill ratio with this fuels, and if you take it very rich, like air fill ratio, say the stoichiometric is 14.7 is to 1. If you have a mixture of fuel and air with the air fill ratio of say 20 is to 1 for gasoline, like 14 is to 1 is stoichiometric, but if you go 16 is to 1, it can still burn. But if you go to say 20 is to 1, it will not burn at all. So this is one. So when you go very lean, it cannot burn. That is the limit. Similarly, if you go little richer, 14 is to 1, it can burn. 13 is to 1, it can burn. But if you go, say, I think 8 is to 1 is the limit. So if you go, say, 6 is to 1, it will not burn at all. So this is the flammability limit. It's a property of a particular fuel. So gasoline will have generally of 8 is to 1 to 18 is to 1, and this limit is because of the pre-mixing of the fuel and air. And if you take a CI engine, we are only injecting fuel in the uh, inside the combustion chamber. So it is all air through the engine combustion chamber, and there is a fuel spray, and with this spray the air is getting entrained, getting mixed, and locally there will be a different flammable mixture. So here if you take AFR, will be infinite because there is infinite because there is no fuel at all. At this central core, air fuel ratio is AFR is 0 because there is no air at all. And around some periphery, there will be some flammable mixture. The AFR can be say 14 is to 1, say 12 is to 1, and so on. In these regions, it can burn. So in case of CA engine, there is you can have any global air fill ratio. So these are whatever I mentioned is a local air fill ratio, but the global air fill ratio can be much different than all these values, and much different than the flammability limits. Only the local air fill ratio matters for the local combustion. So in case of CA engine, it can say go from 20 is to 1 to 100 is to 1. Even at 100 is to 1, the local air fill ratio is still around 14 or 12, where it can burn properly. But for SI engine, this CA engine phenomena is much different than SI engine premix combustion, and we need to stick to the flammability limits of the fuel. In SI engine, for maximum power, the relative fuel air ratio is 1.5, 1.2, 0.8, 0.6. So for maximum power, the relative failure ratio can be 1.2. So within flammability limits, I want to mention for hydrogen, the flammability limit is say 5% to 75%. So that means out of 100 air, 5 portion of fuel still, or it can be like 100 is to say 20 is to 1 to here it is. So it is very less, say 1.2 is to 1 something like that. So this is the flammability limit for a hydrogen. So that means if from the tank, hydrogen tank, and here it is full air in the atmosphere, if it leaks a little, and for a large region there could be a flammable mixture, because here it is AFR is infinite, and here at the periphery it is 5%, and somewhere here inside it will be this region will be say the 75%. So beyond this it is fully flammable, whereas in case of LPG it will be similar to gasoline, say 8 to 18. So then the flammability of LPG, and it leaks somewhere, only a small region will be flammable, and once it is mixed well in the air, it is not flammable. But here, so a large region will be flammable. So that is why hydrogen is more difficult to handle. Next question: for maximum thermal efficiency, the fuel air mixture in SI engine should be lean, rich, stoichiometric, maybe rich or lean.
Lean.
Lean, yes. With rich, the power will be high power, but low efficiency. Stoichiometric is like trade-off between low power and efficiency. During starting, petrol engine requires stoichiometric mixture, rich, lean, any air-fuel ratio is alright. During starting, petrol engine requires stoichiometric, rich, lean, any air-fuel ratio.
So rich.
Rich, yes. Why?
For idling.
Sorry?
For idling.
For idling, yeah. Why rich is needed for idling or starting? To have stable combustion. So during starting and idling, stability of the combustion is of prime concern, because at low speed there is more heat transfer, and then there will be less say heat transfer is high, the mixing is low, because uh, the the RPM is low, and because of the piston velocity will be low, the air the speed at which the velocity at which the air enters everything is low, and because of this the mixing or the kinetic turbulent kinetic energy will be lesser, and this this will attribute to low mixing, and because of this we need to have rich mixture during starting and ending. For petrol engines, the method of governing is hit and miss governing, quality governing, quantity governing, none of the above. It is quantity governing because we control the m dot a while keeping air fuel ratio almost constant. So air fuel ratio is quality of the fuel, or the quality of the mixture. M dot A is change in the M dot A is the bulk mass you are changing, so that is quantity term. Economizer is used to provide enriched mixture during starting, idling, cruising, full throttle operation.
So full throttle operation.
So the economizer device itself is used only for full throttle operation to extend the mixture. When the throttle is suddenly opened, the mixture from the simple carburet tends to become rich, lean, circumetric, not affected.
Yeah, which
How?
because of the our input is given is high.
Input air. M dot A will increase and fuel will start flowing slowly because of inertia of the fuel, and the when the when the throttle is open fully, you will have before the throttle is open fully, there will be some deposition of fuel in the manifold, and when it is open fully, like if it is horizontal, then the pressure here will be higher than the part that it is. So if the pressure is higher, then there will be more deposition, and because of this it will become lean. Next one, the choke in an automobile meant for supplying lean mixture, rich mixture, stoichiometric, weak mixture. Rich mixture. So this is why we use for starting, mainly cold start. Modern carburetors provide the current quality of air fuel mixture during starting, idling, cruising, all conditions.
For all conditions.
And that is the objective of the carburetor. With a simple carburetor we are not able to achieve, but with the advanced carburetors with many fuel and air parts we are able to achieve. A simple carburetor supplies rich mixture during starting, idling, cruising, accelerating.
So idling and accelerating.
Fuel injector is used for gas engine, C engine, S engine, and etc.
CING.
Advantage of air injection system is cheaper fuel can be used, MEP is high, fine atomization and distribution of liquid of the fuel, all of the above. Fine atomization and distribution of fuel. So because while injecting, it is not only fuel that is injected, it is injected along with the air, so there will be high turbulence and high mixing factor. It will become fine droplets from early stage. Otherwise, if it is a solid injection system, it will be a liquid jet initially and then air entrance from the combustion chamber. But with the air injection system, air comes along with it. Commonly used injection system in automobile is air injection, solid injection, combination of A and B, none of both.
Option C.
Sorry, option? Solid injection is commonly used in automobiles. Because air injection, you need to pressurize the air to a very high pressure, and that will take more energy. But in solid injection, fuel injection pressure in solid system is around 200 to 50 bar 30 to 50 bar 10 to 20 respiration bar.
Sir, less than 10 bar.
No, actually solid injection has the highest pressure. Fuel filters do not use generally oil, paper, cloth, wood. Oil is not.
Oil.
Yes. Fuel is injected in a 4-stroke CA engine at the end of suction stroke, at the end of expansion, compression, or exhaust stroke.
Suction stroke. Sorry, expansion stroke.
Fuel is injected at the end of compression or beginning of
Compression stroke.
injection system in which the pump and injector nozzle is combined in one housing is known as
The distributor.
unit injection system. In distributor system, there will be one pump which distributes the fuel to the individual cylinders. If there are say 6 cylinders, so from one distributor unit it goes to individual cylinders, injectors on each cylinder. But in unit system there will be one unit system sitting on for every cylinder, and that will have a cam actuated pump, and then it will have an injector and can be controlled electrically. So it is unit injector system. The most accurate gasoline injection system is direct injection, port injection, throttle body injection, manifold injection.
For port injection.
Actually direct injection, because you can so in case of port injection there will be a manifold deposition, fuel deposition in the manifold, and because of that you might have to compensate for that when you during transient case, like as I said, when you open the throttle and close the throttle, the pressure will increase or decrease. Because of this the fuel deposition will increase or decrease a bit. So you have to every time keep compensating for the deposition, and then it will not be very correct. So the air fuel ratio during transients will not be very correct, equal to stoichiometric. But in case of direct injection, there is no deposition phenomena happening. You directly inject inside the cylinder, so it is more accurate. Advantages of fuel injection in SI engine is low initial cost, low maintenance requirements, increased volumetric efficiency, non-operative.
For A, B, C.
No, actually the initial cost is very high, because there has to be a pump which pumps the fuel to say 50 to 200 bar of gasoline. So this pump is needed, and the injector is electrically actuated, which has to handle all the high pressure, and all this make it high initial cost. And maintenance is also high uh, because of more moving parts and all. The This is strong. This is because of more moving parts of the pump tunnel, the maintenance becomes high. Only thing is volumetric efficiency increases because you directly inject at a high pressure inside the cylinder, maybe after the intake stroke itself. So you have all the mass of the air coming in, and then you inject fuel. So the initially at the end of suction stroke, you have say m dot a, sorry m1a, which is corresponding to the volume at VDC. But in case of manifold injection, you had mass of charge which is m dot ma plus mass of fuel, which totally corresponding to the volume at VDC. So now in the mass of fuel is not added to this, it's not added initially. That means say this would be say 15 is to 1, right? So 1/15th of the volume is consumed by the not exactly, but mass wise 1/15th of the volume is considered is taken by the fuel. But now it is not the case. Even you get more air going inside. Any questions?
No, sir.
You can go to a problem, solve a problem. A simple jet carburetor is required to supply 5 kg of air and 0.5 kg of fuel per minute. So that is 1 dot U is equal to 5 by 60 kilogram per second. 1 dot F is 0.5 by 60 kilogram per second. The fuel specific gravity rho F of is specific gravity of fuel is 0.75. That means rho F is 750 kilogram per meter cube. Air is initially at 1 bar and 300 kilo Kelvin. So that means T atmosphere is 1 bar, T atmosphere is 300 Kelvin. Calculate the throat diameter of the choke for a flow velocity of 100 meter per second. So flow velocity at choke or at of 2 is 100 meter per second. Velocity coefficient is 0.8. Or this. So if the pressure drop across the metering orifice is 0.8 that of the choke. So delta P of the fuel is 0.8 that of the choke is where the air goes. So I write it as delta P. Calculate the orifice diameter assuming CDF equal to 0.6 and normal into 1.6. Now you have a carburetor with a throat. Assuming this is state 1, this is 2. Here the pressure is atmospheric pressure. So P1 is 1 bar and T1 is 300 Kelvin. At state 2, at the choke of the throat, at the throat, the diameter is lesser. And now you have some fuel supply by a closed chamber. Now we need to essentially calculate throat diameter, that is where the air flows in, and we need to calculate the orifice diameter. Can you say how we can find? So for the velocity at the throat, we have this equation from the compressible flow. So C2, that is 100, C2 is equal to Vc is the velocity coefficient into 2Cp T1 1 minus T2 by T1 whole power gamma minus n beta 1. C2 is, we know at throat the velocity, air velocity is 100 meter per second. So this is 100 is equal to Vc is given as 0.8 velocity coefficient, and Cp is not given, but we know the Cp for air, right? Cp for air is 1005 joules per kilogram Kelvin. This is 1005 into T1 is given as 300 Kelvin minus 1 into 1 minus T2 by T1 gamma minus 1 by gamma. So gamma value is given as 1.4, then we have 0.4 by 1.4. Now we can rearrange and calculate P1 by P2. Then we also know P1. P1 is already 1 bar, right? So if you just neglect this, we will calculate P2 in bar. So we take on the other side, and we have 2 into 1005 into 300 into 1 minus P2 power 0.4 by 1.4 is equal to 100 by 0.8 the whole square. So now 1 minus P2 power 0.4 by 1.4 is equal to 100 by 0.8 the whole square into 1 by 2 into 1005 into 300. Now P2 power 0.4 by 1.4 is equal to 1 minus 100 by 0.8 square. So on the left hand side we had 0.4 by 1.4, on the right hand side we made it 1.4 by 0.4. Can you calculate P2?
So I'm getting 2.4.
I'm getting 0.912. Can you check again?
Okay, fine.
Are you able to find it? Or we
That
can.
will be fine.
Sorry?
I'm calculating.
Okay.
Sir, 2.1.
Still 2.1.
Yes, sir.
Okay. Then you would calculate in parts. Can you calculate what is 1 by 2 into 1000 by into 300? What about other person in and organ? Okay. 1.6 1.658 into 10 power minus 6. Okay. Now we will multiply this with 100 square by divided by 0.8 square. 1.658 into 10 power minus 6 by into 100 square by 0.8 square. Point 0.025.
So 0.025.
2591. I will take 4 digits, that's better. And now we have 1 minus 0.02591. Okay.
So it's coming 0.97.
97408. 1409. Now power of 0.974, 1.4 by 0.4.
Zero point 91.
9122, right?
Yes, sir.
Yeah. Are you using this calculator, scientific calculator like this, or you're using
Yes,
mobile?
sir.
Huh?
It's scientific calculator.
Okay. Then you should be able to do in one stretch, no? See, this things, if you know, yeah, right. You should be knowing where to put the braces correctly and where to uh, put everything right, like While you type in calculator, this thing should be there. Put the integer 1.4 divided by 0.4. Then here we put 1 minus 100 square divided by, you start a bracket, 0.8 square into 2 into these things. If you are able to put the braces correctly using a scientific calculator, you can solve this in one stitch. Then that will save a lot of time. You should practice for that. Then I think for gate nowadays you have the online calculator, but this will save a lot of time if you know how to do it in one go. Anyway, so we got 0.9122 bar for the pressure at the throat region, right? Now basically we need to use two, we have both the m dot a and m dot f. So we know m dot is rho a v. We need to use this equation and find the area. We need to find area at throat and velocity at the throat. For air, velocity at throat is already given. We need to find rho only. So to find the rho, we need to use isentropic process, which is P1 V1 power gamma equal to P2 V2 power gamma. So for this we need to know V1. How do you know V1? We know this is P1, atmospheric pressure and temperature. We need to just calculate V1, right? So we can use ideal gas equation, P1 V1 equal to RT1.
MT1.
MRT1.
So MRT1.
Yeah. So if you put a specific volume, then it will be RT1. Right? Specific volume is what? V1 is total volume by mass. So this is equal to 1 by rho, inverse of density. Okay. So V1 is RT1 by T1. What is R for air? 287 into T1 is 300 by pressure is 1 bar, that is 10 power 5. Now can you say what is V1 specific volume at state 1?
Zero 0.861.
0.861 meter cube per kilogram. And now we can find rho 1, which is 1 by V1. 1.16 kilogram per meter cube. Now to put this in one, we have P1 V1 power gamma equal to P2 V2 power gamma. Now V2 can be found. P1 is 1 bar into V1 is 1.165. V1 is 0.861 power gamma is 1.4 equal to P2 is 0.912 bar into V2 power gamma. Now V2 is equal to 0.861 divided by 0.912 power 1 by 1. Can you get this? Or I can write in steps if you are not able to follow. Can you calculate V2?
Sir, 1.
1?
Sir, power is for 861, right?
No. See, we had this power 1.4 and divided by 0.912, and then here we had 1.4. Take in, multiplying this by 1 by, take in power of 1 by 1.4 on both sides, right? We will have V2, then this will be 0.861 and divided by 0.912 power 1 by 1.4. Do you get this? Satik, are you able to follow this?
Yes, sir. So 0.919.
Is it 919 or 969?
So 919.
Okay, 919. Unit is meter cube per kg because this is specific volume. Now rho 2 is 1 by V2, and that is
1.087.
87 kilogram per meter. Now M now M dot AR is rho 2 A2 V2. M dot A is known, that is 5 by 60. Yeah, 5 by 60. And rho 2 is, we just calculated 1.087 into area 2 is 5 by 4 into diameter of the throat, right? So that is d2 into velocity is 100. Now d2 can be calculated. So that is 5 by 60 into 4 into 1 by 100 into 1.0875 whole root.
So 0.031.
0.01. What is the unit?
Sir, mm or
This is in meters, so in mm it will be 31 mm. We have used everything in SI unit, so we have got this diameter in SI. Okay. Now next is to find the diameter of the orifice. So this is the diameter of the throat for the airflow. Now we need to find the diameter of the orifice. For orifice, again we need to have same m dot a, m dot f is equal to rho a e. Now rho is known, rho of the fuel. Area of the orifice we need to find, and the velocity of the fuel is we need to calculate. For velocity of the fuel, we know this one, that the change in pressure of the fuel is 0.8 times the change in pressure of the air. So that means delta Pf is equal to 0.8 delta Pa, and this is 0.8 into change in air pressure is, initially it was 1 at 1 bar, and later it became at throat it became 912 bar. So this is 0.912. Can you calculate this?
0.0704.
Yes, 0.0704 bar. So this is a change in pressure. Now across orifice we need to find the we know the delta pressure across the orifice for the fuel. We need to find the velocity of the fuel. How do we calculate? So df is equal to 2 delta pf by rho. So across orifice, if you want to calculate the velocity across with the pressure difference across orifice, it is under root 2 delta p by rho, right? So then we have 2 into delta p is 0.0704. 0.0704 into 10 power 5 because we need to have in SI units, and then rho is 750. The specific gravity is given as 0.75, so the density is 750 kg per meter cube. Can you calculate velocity of the fuel?
4.33.
What is the unit?
Meters per second.
Okay, meter per second. Now we got the velocity of the fuel, and to find sorry, sometimes okay. So m dot f equal to we need to put the coefficient of discharge of the orifice into rho a v, all of the fuel. So m dot a f is given as 0.5 into by 60. CDF was given in the problem, that is 0.6 into density is 750 into area of the orifice, that is pi by 4 d naught square into velocity of the fuel is 4.33. So now to calculate d naught, we will have within the root 60 into 4 divided by 0.5 into 0.6 into 750 pi into 4.33. Can you calculate the diameter?
So 0.28.
0.28. Seems very high. Oh, sorry. So it will be 0.5 into 4 divided by 60 into 0.6 into 750 pi into 4. Sorry.
2.33 into 10 power minus 3.
10 power minus 3, okay. So this is 2.33 mm. So this is the diameter of the orifice for the fuel. So this is the orifice diameter for fuel, and this is the throat diameter. Throat diameter we saw that is around 31 or 32 mm. 31 mm. For this we got for 2.6 mm. Do you have any questions?
No, sir.
We have less time, but we try to solve this problem. Determine the change of air-fuel ratio in an airplane engine carburetor when it takes off from sea level to a height of 5,000 meters. Carburetor is adjusted for 15:1 ratio at sea level, where the air temperature is 27 degrees Celsius, pressure of 1 bar. Assume the variation of temperature of the air with altitude at T equal to Ts minus 0.0065 H, where H is in meters and T is in degrees Celsius. The air pressure decreases with altitude as per the relation H is equal to 180 to 100 log base 10 1 by P, where P is in bar. Evaluate the variation of air-fuel ratio with respect to altitude in steps of 1000 meter on the trend. Show the variation on a graph and discuss. So the variation of temperature of is given. So with altitude, H is altitude. With this temperature changes given by Ts minus 0.0065 H. So given what is Ts? Okay, Ts is 27 degrees Celsius at sea level. Okay. So Ts is 27 degrees Celsius. And the air pressure decreases with altitude as per the relation. Okay. And that relation is H is altitude, and it is 192 W0 log base 10 and by T, where T is in bar. Evaluate the variation of air-fuel ratio with respect to altitude in steps of 1000 meters. Any idea how we can solve this? So we have this simple carburetor, state 1 and 2. We can get this relation. So for air fill ratio, we need m dot a by m dot n. M dot a is rho a density of air, area of the air part, that is the throat, into velocity of air. Similarly for OF, AF, VF. Now the area will not change with respect to altitude, right? And rho f will change with altitude? No, because the density of fuel is almost constant. Rho of A will change because we have seen that it is P by RT. So pressure is also changing, temperature is also changing, so probably rho will change. Does the velocity of VA, VF changes? In VA is proportional to the root of velocity, temperature, right? And pressure ratio wise, it doesn't affect. And similarly for VF, so it is coming from this relation, and for this VF it is under 2 delta PF by rho. So your rho doesn't change, delta PF doesn't change. So finally we have AF for 1 by AF by 0. So AF0 is the air fill ratio at ground, that is 15:1. And A for 1 is something that is changing. So here it is m dot A1 by m dot F1 by m dot A0 by m dot F0. So we saw these parameters doesn't change, and VA and VF doesn't change significantly. VA can change with respect to the root of T1, but otherwise it doesn't change. Other things will change. So we can have here rho A1 into VA. So in VA there is only T1 term that comes into picture. So maybe here VA naught root of T0, and rho of A is P by RT, no? P by RT. So R is also constant, only P and T matters. And here if you have PA by T1 root of T1 by P naught by T naught root of T naught. Now we will have P1 by P naught into root of T naught by T naught. So now we know zero conditions are there at sea level. So we know P naught and T naught. At different altitude, you can calculate P1 and T1, and then keep calculating the ratio of air fill ratio. So that means how much difference from 15:1 is what we can calculate. So this we can solve in the next class. We have only 5 minutes here. If you have any questions, if there are any previous questions, then you can discuss. I would also like to know about you. You both are taking this course. Where are you from? You are doing BTech or MTech or?
Here I'm from Chennai. DE Ahmed.
Spartik.
Second year.
Oh, you are from Chennai.
Yes, sir.
Okay. And you are doing B Aeronautical?
Yes, sir.
Okay. Hemanathan is also from Chennai. B. Okay. Swatik is aeronautical. Hemanathan is mechanical. Okay. Which college is it, sir?
Sir, I'm from Satyabama College.
So Swatik, you okay? You both which semester you are in?
Sir, fourth semester.
Okay. So you are crediting this course for your university exams, or like in your mark sheet, this NPTEL course will be included?
Yes, sir, in the professional course.
Okay. Okay. So based on this exam you write for NPTEL, that will be taken in the degree mark sheet, right?
Yes, sir, it will be included for
Okay.
the credits.
And your Satvik is from Tamil Nadu itself or somewhere outside?
No, sir, I'm settled here, sir, in Chennai.
Okay. Okay. So I am not sure if you do you know where I am from?
No, sir.
No, I'm also from Chennai. Like hometown is Tirunelveli, but I'm currently in Chennai. I'm doing PhD in Indian Institute of Technology, Madras. So if you want to, if you're very interested in looking at my lab, I'm working on IC engines lab. So my project is on hybrid powertrain, developing hybrid powertrain for two-wheelers. So if you're interested in visiting our lab, you can drop an email. Then we can fix a time and you can meet if you're more interested in seeing the lab.
Okay, sir.
You have any questions or you can close the meeting?
No, sir, not.
Thank you for joining. See you next time.
Thank you, sir.